Okay, let's start this class. So this is the week 10th of the course Physics of Materials, and we will have two more classes after this one. Okay, so we have 10 questions also in this class. So let's go ahead with them. The first question is: the first Brillouin zone is the first Wigner site cell about which lattice point? Reciprocal lattice point, real space lattice point, imaginary lattice point, or double lattice point. So there are two terms here. One is the Wigner-Site cell, and the second term is Brillouin zone. So we'll define these terms here. So Wigner-Site cell is the it is a region in space. This space can be both real or reciprocal. That is closest to that lattice point than to any another lattice point. So what it means is, let's say we have a lattice. It may be in the real space or reciprocal space. So let us consider this particular atom in the center. So we have to find out the region in space that is closest to this particle compared to any other lattice point. So that will be exactly at half distance of this, between these two particles, half distance, between these two particles, half distance. So half of with this one and half with this one. So this one is the Wigner site cell of this particular lattice point with this area. So now if this lattice, if this is in the reciprocal space, then we will call this Wigner site cell as the Brillouin zone. And when it is with respect to the closest located atoms, for example, for this atom in the center, this is the closest, we'll call it the first Brillouin zone. This is the first Brillouin zone. So the first Brillouin zone is a Wigner site cell about a reciprocal lattice point. So Wigner site cell is always a primitive cell. With what it means is that it will always contain only one lattice point. So I'll just write it here. So primitive cell. contains exactly one lattice point. So the answer to the first question is reciprocal. So we'll move on to the next question now. In a in two dimensions, Wigner side cell about a lattice point is generally of how many sided except for square and rectangular geometry. So in this question we will draw it and we will figure out that for a random two-dimensional lattice that is not square or rectangular, what how many sides are there for beginner side cell. So let us first consider the square or rectangular lattice and try to find out what is the beginner side cell of this. So we'll draw it here. So let us again take this point and let's draw the beginner side cell. So so these are the closest located points. So we'll draw for them. So for the cell on the top, this will be the exactly half of the space dividing between them. With the left, it will be this one. With the bottom, it will be this one. With the right, it will be this one. So the beginner side cell will be this unit. Therefore, for square and rectangular, the beginner side cell has 4 sides. Now, for a random square rectangular, for a random unit cell, it will look something like this. So we'll again try to draw the beginner side cell for this one. So the closest located atoms are this one, this one, this one, this one, this, and this. So let's draw for it. With the top, this will be the region dividing the space in half. With the left, it will be this region. Okay, we'll first draw. With the bottom, it will be this region. With the top left, it will be this region. With the bottom left, it will be this region. Here is like this, cutting in half. This here. So the region in space will look something like this. Six sides. Answer is option B, 6. In two dimensions, beginner side cell about a lattice point is generally six-sided, except for square and square rectangular geometry, where there are 4 sides. Okay, let's go to the third question. The Bragg plane is a perpendicular bisector to which of these geometrical entities that joins the origin of the reciprocal space to any lattice point? So We'll also try to understand this with the help of a diagram. We'll draw this out to solve this question. So this is what this is the origin. Let's say this is the origin, and this is an evolved sphere, so with center somewhere here, and this is the reciprocal lattice point with lattice parameters b1 star and b2 star in the reciprocal space. So to we can draw the incoming and outgoing wave vectors. Let's say this is the incoming wave vector, and for the condition of diffraction to take place, we will have another wave vector like this, and the difference of this has to be a reciprocal lattice vector. So we'll label them. Let this be Ki, this is be Ko, this be capital K, and we'll name them A and B. So the condition for diffraction, as we had discussed in the last class, condition for diffraction, the difference of the incoming and the outgoing wave vector should be a reciprocal lattice vector, which when written is like K out, the outgoing wave vector minus the K incoming wave vector should be equal to a reciprocal lattice vector. Now now the Bragg plane is defined as the Bragg plane is defined as the line which bisects the reciprocal lattice vector. So it will be something like this. So this is the Bragg plane. So Bragg planes are perpendicular bisector to the line that joining the origin of the reciprocal space to any reciprocal lattice point. So which if we draw, it looks something like this. So there are two reciprocal lattice points at 0 and B, and the Bragg plane is a perpendicular bisector which connects these 2 points. So the answer is B line. And what is the significance of this Bragg plane? Like, why do we care about the Bragg plane? So we studied about the Brillouin zone. So the boundaries the Wigner-Site sail are same as the Bragg planes. The Bragg planes define the boundaries of the Wigner-side cell. So we can redefine the Brillouin zone, which we had done in the first question. So if we want to redefine the Brillouin zone, this is the region bounded by the nearest collection of Bragg planes around a reciprocal lattice point. So we define the cell as the region dividing the space in half. And if we see this, the Bragg plane is defined as a perpendicular bisector. So it always divides the space in half. So Brillouin zone are the boundaries of the Wigner-side cell. Now, if we look at this diagram, we can see some interesting like uses of the Bragg plane. So we see that. Okay, so first I'll write down the statement. The Bragg plane is important because whenever a Bragg plane touches one end of a wave vector, the condition for diffraction is automatically satisfied. So corresponding to the evolved sphere respect to that wave vector, the condition for diffraction is satisfied, but only for that wave vector. So we'll try to explain this statement. This is the one of the important reasons why we study about Bragg planes. So if we see here, we find that we find that Bragg plane always passes through the center of the evolved sphere. So here is basically the point A. And they are always the perpendicular bisectors, which is the definition. Perpendicular of reciprocal lattice. So we see here that the Brillouin zone will always pass through the center of the circle, which is A. It is always, and if it is in the edge of the, if it touches a wave vector, let's say it touches the ki wave vector, and since it is a perpendicular bisector of this reciprocal lattice vector, which is capital K, we see that automatically the point, this point, the outgoing wave vector has to touch a reciprocal lattice vector. So just because, this is just because by geometry considerations, if if the if the bragg plane touches the end of a wave vector, and if the uh, and it's just because it passes through the origin, and if we draw the revolved sphere, and if the diffraction is satisfied, then the outgoing wave vector must touch a reciprocal lattice point. This is why the concept of bragg plane is important, and we will be reading about it. I hope the importance of bragg planes is clear. So it also depends. For example, uh, there's also a diffraction condition for this point, and then we can draw another wave vector, which is the color of the pencil. So like in this point, so we'll again have a this is a uh, reciprocal lattice vector, and it causes a diffraction. If we try to draw the reciprocal the bragg plane, it will be perpendicular to this. It again passes through the center of the evolved sphere. If it touches the wave vector ki, which is common to both these cases, and then automatically, since the capital, let's say K2, is a reciprocal lattice vector, which the bragg plane perpendicular bisects. So this point C is automatically, it has to be a lattice point, reciprocal lattice point, because the K2 is a reciprocal lattice vector, and so AC must be a vector which touches the bragg plane at point A, and the other point touches the wave vector, the reciprocal lattice point, resulting in diffraction. Okay, so we'll move on to the next question. The first Brillouin zone can be defined or stated as the region before crossing any bragg plane in any direction, region before and after crossing any bragg plane in x direction, any region in space that can be reached from origin without crossing a single bragg plane. It is the region before second and third bragg plane. So we saw it in this figure that if it is a if we had mentioned here also, if it's a reciprocal lattice point, then these planes, as we have defined later in the third question, these planes are bragg planes. In this case, they are the first bragg planes because they are with respect to the closest neighbors. So the first Brillouin zone is the region before the first bragg plane. Is the region before the first bragg plane. So so the option region before crossing any bragg plane in any direction, this option A is correct. Region before and after crossing any bragg plane in this x direction. So I mean, it has to be in all directions, x, y, z coordinate for a three-dimensional system. So option B is an incomplete answer. Any region in space that can be reached from origin without crossing a single bragg plane. So yes, so it has to be before the single first bragg plane. Even option C is correct. Region before second and third bragg plane. So we have both the first and second Brillouin zone before the second bragg plane. So if this answer was before first, then it would have been correct, but this is wrong. It is the region before the first bragg plane. Okay. Let's move to the next question. Arrange the following given points in the right order to draw the first Brillouin zone. What is the order of this uh, sequence of exercises that we need to perform? So we have to start with the identify the real lattice first, because that is a starting point in the real space. The first step is to find out the real space lattice. So let the real space lattice be a rectangular lattice that looks something like this. If these are the A1 and A2 real space lattice vectors. Real space. So the first uh, activity is to identify the real lattice point. The second is to convert it into reciprocal lattice so that we can draw the back planes of the Wigner side cell. So the next step, this is the first step. Now, how will the reciprocal lattice of this lattice of the in the real space look like? It will look something like this. Since it's the reciprocal, the lengths are the reciprocals of the real space. So in this one, along the A1 axis, the width was smaller than in the A2 axis, but here it's reciprocal, so it has flipped. So now the length in the reciprocal space along the B1 axis is larger than in the line than along B2 axis. So B1 and B2 are reciprocal space lattice vectors, unit vectors. This is the reciprocal space. This is the second step. Now we have to draw the Wigner cells corresponding to this, or the back planes corresponding to this. So let this be, let me import the figure. Okay, there's something. So I have taken the same figure again here. So this is the step 3. We have B1 and B2 vectors as in step 2. So what we do here is we now draw the back planes or the Wigner side cells corresponding to this. So let's say we'll take and consider this lattice point in the reciprocal space. So it will the Bragg planes will look something like this, or the Wigner side cell will look like this. It divides the region in. So if it's a Bragg plane, means this space is there. It has to be the perpendicular bisector of this lattice vector, reciprocal lattice vector. And if it's a Wigner side cell, so this space in between is divided in exactly half by this line, by this plane. So both of them are the same geometrical boundary. That's why We'll draw the bragg plane or the reciprocal lattice, the Wigner's side cells by drawing lines at exact half distance. So on top of this will be the line, on bottom this will be the line, on left this, on right this. So we can now connect the boundaries. So the third step, you connect the you draw the Wigner side cell or the bragg planes, and then you have an enclosed boundary, which is the Brillouin zone. This is the Brillouin zone. So third step is that you either identify the bragg planes or the Wigner side cell, both of them are identical, and when you complete the geometry, we get the first Brillouin zone. So the options, so the correct answers are 1, 2, 3 and 5, or 1 to 4 and 5. Both of them are correct answers. 1 to 3 and 5, 1 to 4 and 5. Both options A and B are correct. This boundaries the boundaries are the bragg planes. Actually, this entire area is the Brillouin zone, so I should write in green color. This is the first Brillouin zone. I hope this is clear. If not, you can ask me in the NPTEL forum. Okay. We'll move to the next question. The second Brillouin zone is fragmented in how many fragments? Like 6, 4, 6, 6 or 4. So the second Brillouin zone is fragmented in dash fragments, while the dashed Brillouin zone is fragmented into 8. What is the correct answer? So we know that for the square lattice, the third Brillouin zone has 8 fragments. So the second Brillouin zone will have how many fragments? 4 fragments. So we will draw and find it out. I will also show you. So let's see the figures. That will be much more easier to understand, I guess. So this is what the Brillouin zone of a square lattice looks like. So this is a square lattice. So the way it is drawn is, so I will again try to draw the lattice here. So to draw the first, so we'll draw the nearest neighbors here, the bragg planes here. So if we take the center one, this, then these two are bisected. So if it's square, it is this is the bisector. If then this, sorry, with respect to the diagonal, this one. That is how you can keep on drawing. So in this figure, this is the first Brillouin zone as we had discussed in the previous question, and then these elements are the second Brillouin zone. This is how this Brillouin zones are drawn. So basically, there is a reciprocal lattice point here, 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 and so this is exactly half of this. Then this is divided at this place, and so that is how it is drawn. So we see that the first Brillouin zone has only one segment. The first Brillouin zone has one segment. The second one has two segments. The third one has one, two, three, 4, 5, 6, 7, and 8. So for a square lattice, the first Brillouin zone has only one segment. The second Brillouin zone has 4 fragments. The third Brillouin zone has 8 fragments. That's why the answer is 4 and 3. Let us also consider what other Brillouin zone looks like. This is only for square lattice. If we consider rectangular lattice, then we see that the shape of the Brillouin zone changes and also the number of fragments changes. So if it is this is for a rectangular lattice. Reciprocal space. Here we see that the first Brillouin zone has only one fragment. The second one has 4 fragments. The third one has 10 fragments. So we'll write it down here. Has 1. Second Brillouin zone has 4. Third Brillouin zone has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we write it down here, the first, second, and third. First one has 1, second one has 4, the last one has 8. So the number of fragments of the Brillouin zone depends on the shape of the reciprocal lattice. A square lattice will have different number of Brillouin zone fragments compared to rectangular lattice. So here it said that it had 8 fragments in the third one. That's why we know that this is only for square lattice. Now let's also consider a hexagonal lattice because this is interesting. So if we see the hexagonal lattice, the first Brillouin zone is again only one fragment. So always, irrespective of the lattice, the first Brillouin zone doesn't have is not fragmented. It's only one regional space. It's only the higher order Brillouin zones which are fragmented. So first one has only 1. The second one has 6. Third one has 6. So the first Brillouin zone is only one unit, one region in space. It's not fragmented. Second Brillouin zone has 6. The third has 6. As we can see, the number of fragments are a variable. It depends on the lattice system. The answer is D here because it's for a square lattice. Okay. Let's move to the next question. So the rhombic dodecahedron is the first Brillouin zone of FCC lattice. Is it a true or a false statement? So before answering, let's see what exactly is this shape called a rhombic dodecahedron, because it seems like a complicated name. We generally don't talk about these kinds of structures. So this is what rhombic dodecahedron looks like. So it consists of 12 congruent. It's a polyhedron, 12 congruent rhombic faces. So if you open up the crystal, then you can you will get that it's a structure like this that has 12 rhombic faces. This structure is called rhombic dodecahedron. Another structure that we will be talking about is this structure. This is called truncated octahedron. So we know that an octahedron has, from the name octa, it must have 8 parts, 8 faces. So it's an octahedron. And when you chop off the pointed edges, so you'll get a structure like this. If you like cut along this planes and also like here and on the back side, you will have 6 squares. So that's why this is called truncated octahedron. So again, if you open up this structure, it looks something like this. So this rhombic dodecahedron, I'll write it down in the bottom. Now let's consider two crystal structures. Let's say if the real space crystal structures, if BCC real space crystal structure, then in the reciprocal space we have the FCC structure. If you have the FCC in the real space, then you have BCC in the reciprocal space. So in the case of BCC, we know that there is an atom in the center, which is, and then there are 8 atoms along the in the corners. So if you would have drawn it, it would have looked like an octahedron. But there are also atoms that are located on the unit cells, like in the on the top, facing each of these faces. And when you draw the black plane there, you get these truncated structures. So this blue lines are the bragg planes corresponding to uh, the unit cells that are located adjacent to each other with the faces touching each other. Uh, these are the in the reciprocal space, the uh, the bragg plane and between the two body centers. So in the reciprocal space, you will have the Brillouin zone, which looks like a truncated octahedron. And it's a little bit difficult to imagine, but you can also spend some time and try to understand how this kind of a Brillouin zone is formed. Basically, you have an FCC structure, and you have to find out the bragg planes that are intersecting the face center with each of the other face centers and at the FCC unit cell. And if you do that, you will see that the Brillouin zone looks like has a structure like this, rhombic dodecahedron. So uh, this is for FCC in reciprocal space, but BCC in, okay, it's already mentioned there. So this rhombic dodecahedron is for FCC in the reciprocal space, which is actually BCC in the real space. So rhombic dodecahedron is the Wigner sites Wigner sites of FCC, but Brillouin zone of BCC. I hope you understand this. So if you, this is like the Wigner sites, and this is the Brillouin zone. So rhombic dodecahedron is the first Brillouin zone of BCC structure. It's a Wigner sites of FCC structure. The answer is false. I hope it's clear, because Brillouin zone is the Wigner site cell in the reciprocal space of the reciprocal lattice. Of FCC, Brillouin zone of FCC. Okay, let's move on to the next question. Which one of the schemes is based only on the first Brillouin zone? Extended zone scheme, repeated zone scheme, reduced zone scheme, and Venn diagram. Yes, Chandru, you're correct. The answer is reduced zone scheme. Do you have any questions from any of the previous questions? Any doubts or anything? You can ask me if you have. Okay, thank you. So these are what the zone the zone schemes look like. So this is called the extended zone scheme. So basically what we do here is that you draw, so we know that E is proportional to k square, E is equal to h cross square k square by 2m. So if you draw the energy as a function of k, it should be a parabola. It should be like this. But what happens is that there is diffraction that occurs along this Bragg planes, and because of this diffraction, the traveling waves are they are unable to travel. They become standing waves at these Bragg planes. For wave vectors corresponding to these Bragg planes. That's why you then have a plateauing that takes place, and we have end up with a structure like this. This is the extended zone. Oh, sorry, extended. This is the extended zone. Now here we have taken this origin. So the choice of origin here is arbitrary. Okay, and then we have these terms called pi by a and 2 pi by a. So we'll just spend a minute to explain in brief what it means. So let's say we have the same square lattice that we had considered earlier. So we know that if the wavelength is lambda in real space, it becomes 2 pi by lambda in reciprocal space, and we call this is the magnitude of the wave vector. So if the lattice is a lattice parameter is a, the lattice parameter in the real space is a, then in the reciprocal it will be 2 pi by a. So what is the lattice parameter? This is the lattice parameter. So I will draw it here. So let it be, so a1 and a2. Magnitude of a1 is equal to the magnitude of a2. Let it be is equal to a. The units of a's in the real space is in the length units. So now if you draw it in the reciprocal space, again you will get a square lattice. So this is real. In the reciprocal space it will look exactly the same. Because it's a square lattice. But the distance, the lattice parameters, which are now b1 and b2, we take the magnitudes of this, there will be 2 pi by a in the reciprocal space. It's identical to this one. The lambda becomes 2 pi by lambda, so lattice parameter becomes 2 pi by a. So here, if this was a, this is now 2 pi by a. Now if you draw Bragg planes here, they will intersect this. So this will be the Bragg planes. So if you consider only the x-axis, this is, if this is 0, this is pi by a, this is minus pi by a. So the Bragg planes are located at a distance of pi by a. That is what is happening here. We see here the Bragg planes are at pi by a. I hope it's clear. Then, but so that is where we have this pi by a in the x-axis and 2 pi by multiples of pi by a in the x-axis. So like if now, okay, for completion, the second, if you draw it, it will look like this. So if this is pi by a, this is 2 pi by a, and so on and so forward. That's why we have like 2 pi by a, 3 pi by a, these kinds of values. So the choice of origin is arbitrary in the extended zone scheme. However, due to symmetry, we know that each lattice point is the same. So we know that due to symmetry, each lattice point is identical. So basically what you can do is that you can draw parabola at each of these points. And then so now if you will have a, to connect them, you will have a figure like this. Something like this. Now when you do that, when you draw it like that, and then there are like diffraction in the back planes, you will get a structure like this, a figure like this, because each lattice point is identical. So again, is that there's a lattice point at 0 and this lattice point at 2 pi by a, which are here. So this lattice point is 0. This lattice point, where did it go? This lattice point is 0. This is 2 pi by a, and this is the corresponding E versus K diagram. So we see it. We have obtained this by drawing a parabola at each of these lattice points, and what we get is the periodic zone. So what is happening here? The EK diagram is repeated at each reciprocal lattice point. Now, since it is identical, we see that it's a repeating diagram. It will go until infinity. So what we can do is that we can just consider a small region of this, which will consider have all the information. So we can just take this space and then plot it. Then we'll get what we have here in the bottom. So this is called. So you have just displaced it. So we have just taken this part. It's a repeating diagram, and what we have here is called the reduced zone scheme. So all the information is between minus pi by a and pi by a in the reduced zone scheme. So yeah, right. So the first Brillouin's zone is so the reduced zone scheme is based only in the first Brillouin zone. So in the first Brillouin zone, it's like from minus pi by a to the plus pi by a. This is the minus pi by a to plus pi by a. is the limits of the first Brillouin zone, and all the information is contained here. And we will use this diagram. We call it the reduced zone scheme. We have one last question. Okay, we have two more questions. So the forbidden and the allowed energy bands are decided based on which of these conditions? Diffraction, refraction, interference, and reflection. So we saw in the previous diagram that there is a diffraction that is taking place along the Bragg planes. So if we again draw it here, so let's say this is pi by a, let this be 2 pi by a minus pi by a and minus 2 pi by a. The axis is energy, axis is the crystal momentum, sorry, the wave vector. So and then there is initial, if there was no diffraction, it would look something like this, a parabola. But because of diffraction, what happens is that, okay, I'll just draw it here. It should have appeared like this, but instead it appears something like this because there is diffraction taking place here. And so on and so forth. So what happens if you now draw here? This, if you now draw here, then so we can draw bands here. So since the EK diagram exists only in this space, only in this uh, range of energy you can get the electrons. So this is the allowed regime, and but these are the forbidden regimes of energy. So there is diffraction, at Bragg planes. So the answer is that we have the band diagram with the forbidden and allowed energy levels because of diffraction condition. The answer is option A. The traveling waves become standing waves at this Bragg planes. I will just write it down for future reference. The traveling waves of nearly free electrons undergo diffraction at the Brillouin zone boundaries, which are nothing but the Bragg planes, and this results in standing waves. I hope this is clear. So we have one last short question to end this class. Okay. So to choose the right statement, the statement is the Brillouin zone of the same order are obtained at different locations. What is the reason? Is it because Brillouin zones fragmented, or the Brillouin zone is always continuous as the order increases, but may be fragmented when it is the first form. So we saw here, we have discussed this question in detail here. So we see that the first Brillouin zone, irrespective of its hexagonal, rectangular, or the square, the first Brillouin zone is not fragmented, whereas the higher order Brillouin zones are always fragmented. For example, the second order has 4 fragments in square. It has 4 fragments in rectangular, but 6 fragments in the case of hexagonal. So the Brillouin zones can be fragmented, which is why they can be obtained at different locations. So option A is correct. Is always continuous. So it is Brillouin zone is not continuous always, because we just saw that it is fragmented for higher order Brillouin zones. So the option B is wrong. So only option 1 is correct. I hope this is clear. The Brillouin zone is fragmented only for second and higher orders. The first zone is always continuous. Okay, so this is all. Will there be any characteristic changes in the different fragments of Brillouin zones? So as we see here, no. So uh, so all the information data is available in the first Brillouin zone itself. We can get all the relevant data from the first Brillouin zone. We do not need to go to higher Brillouin zones to understand any different physics. This is the first Brillouin zone. These two. So and then like beyond this, you have other Brillouin zones. There is no characteristic. There will be no characteristic change. All are identical. Okay, thank you. Okay, so I think we have crossed the 1 hour limit. You may have other classes, so I'll stop the recording here, but we can keep discussing if you have any more questions.